All right, I hope, maybe I should reboot my computer, I don't know. I hope we're good. Okay, so today we're going to get into Chapter 9. Okay. So this is more hypothesis testing. And confidence intervals. Okay. But this time we are dealing with numeric variables. Okay. So last week, Chapter 8, we did a hypothesis testing, but it was all for categorical variables, and you were dealing with proportions, okay? So just as opposed to last week, we did Chapter 8, categorical variables, and proportions, okay? So when you have categorical variables, you measure using proportions. When you have numeric variables, you will be doing measurements with means, okay? So this week, we will do Chapter 9. We're dealing with numeric variables. And we will be dealing with means. Okay? Okay, before we get into the nitty-gritty of hypothesis testing, I want to make sure we can use the t-table, okay? Use of the t-table, okay? We are going to use the t-table for two types of problems, okay? So pull out your reference tables, and the last sheet is Table 4, okay? And it says T distribution critical values. So pull that out, and we will we'll go through it. If it says Table 4, T distribution critical values, that is the t-table. All right? Okay. So it should look like this. This is your t-table. Now, in this chapter, we have two types of problems, okay? Well, actually 4 types of problems, but I'm going to split them into confidence intervals. We're going to have confidence intervals. And we also have hypothesis tests. And for both of those problems, you are going to need to use the t-table. Okay? So in confidence intervals, we use the t-table to pick t star. Okay? So we're going to come up with a value called t star, and we use the table to pick that. Okay? The choice of t star depends on 2 things. Okay, so the first thing is the confidence level. And the second thing is the DF, which stands for degrees of freedom. Okay, did everyone get that down? Confidence level, Degrees of freedom. So we're going to use the t-table to pick our t star. And our choice of t star depends on two things: the confidence level and the degrees of freedom. Okay, so for example, let's say we want to make a 95% confidence interval, and later on today I will tell you how to determine degrees of freedom. But let's just say we have 9 degrees of freedom. Okay? Our t star will come from the table, and our t star is equal to, so let me just put this over here. What you're going to do is you're going to find the column heading that says 95%, and you go to degrees of freedom 9, and you will use the value 2.262. So our t star is 2.262. Okay, so somewhere in the problem it's going to state 95% confidence. Okay, somewhere in the problem. So let me just write that. Okay, this comes from the problem. And then degrees of freedom, I will teach you how to calculate your degrees of freedom. It's very simple. Okay. But this also comes from the problem. Degrees of freedom, also in problem, maybe one step to figure it out. Okay? So all you do, 95% confidence. So on your t-table, at the very top it says confidence level, and we go to 95% confidence. Sorry, let me fix my color again. 95% confidence, and then we have 9 degrees of freedom, so we just go to the row where DF, degrees of freedom, is 9, and we pick 2.262.
On the right side of the screen, what does it say in red?
Comes from problem. Comes from the problem. Okay, so we use 2.262. Okay, so just quick check. Let's say you want to make 99% confidence interval, and you have let's say 56 degrees of freedom. Okay, now if your degrees of freedom is not listed in the table, always round down. Okay, so if DF is not in the table, always round down. Okay, so you want to make a 99% confidence interval with 56 degrees of freedom. What is the t star that we will use? Okay, so we go to 99% degrees of 99% confidence. It's the second to last column, and I'm going to look up 50 degrees of freedom, not 60, because we always round down. So we're going to use 50 degrees of freedom, and my t star is going to be 2.678. So always round down. So in this case, use 50 degrees of freedom. Yes, David, you have a question?
Sorry for constantly bothering you, but why would you round down even if it's higher than 6?
It's the rule. It's a safety precaution. Okay. So, for example, if your room has 56 chairs in it, and you can invite either 50 people or 60 people, how many will you invite? 50, right? So it's kind of like that. It's a safety precaution. We always round down. Not everything works that way, but in this case, this is what we have to do. Yes?
Can you have a degree of freedom lower than 1?
You cannot have a degree of freedom lower than 1. Okay? So, degrees of freedom, I can tell you where it comes from, but I don't think you guys will care. So, oops. Actually, let me save this as XL10. What is this? May 26. Slider 1. Okay, so that is one use of the t-table. Is that okay with everybody? It's not too bad. Okay, the use of the t-table for the hypothesis test, this is where it gets a tiny bit trickier, okay? So in a hypothesis test, you're going to do your calculations, okay? You do your calculations, and then you use your t-table to figure out your p-value, okay? So just like when you did hypothesis tests on today's quiz or last week's homework, you did your calculations, you arrived at a test statistic, but that wasn't the answer you're looking for. You use your test statistic to get to look up in the z-table to get your p-value, right? So same idea, you do your calculations, you get a test statistic, but for these problems, you look your test statistic up in the t-table to get your p-value. Okay, so you do your calculations, get a test statistic, and then you look up the test statistic in the t-table to get your p-value. So it's very important, don't mix these two things up, okay? Confidence intervals, this is the process you use. For hypothesis tests, this is the process you use, okay? If you're doing things like hypothesis test stuff for confidence intervals, it's going to mess you up. If you do the same thing for confidence intervals for hypothesis tests, it's going to mess you up. Keep these separate. So anyway, you've done your calculations, you get a test statistic, you're going to look that up in the t-table. So your test statistic, let's say, from your calculations, so example, okay, so your calculations lead you, say you have 10 degrees of freedom, and your test statistic is equal to 2.81. Sorry. Okay. 10 degrees of freedom, your test statistic is 2.81. All right, this is how we get our p-value from there, okay? So first we have to get, well, I'm sorry, we're going to get our tail area, okay? So we're going to take this number 2.81, and we're going to come over to our table, and we're going to go to the row where we have 10 degrees of freedom, okay? So in the problem, we figured we have 10 degrees of freedom. We come to our table, we say, I got 10 degrees of freedom. So I'm going to be in this row right here. And then I'm going to say, all right, if I had to put this number 2.81, where would it fit? Okay? So 2.81 fits in between is bigger than 2.764, but smaller than 3.169. Is that okay? So what did I say? 2.81. So 2.81 fits in between here and here. Okay? we're going to get our tail areas, we look at the right tail probability at the very top of the column. And so we see 0.01 and 0.005. Is that okay? So my tail area is between 0.010 and 0.005. Okay, so I'm just taking the column headings of the columns where 2.81 is smaller, okay? Or is between. So 2.81 is in between these two columns, so I take those two column headings as kind of boundaries for my tail area. So we don't get a specific exact tail area. We just say my tail area is between 0.010 and 0.005. Okay? Or I can write it this way. My tail area is less than 0.010, but greater than 0.005. Is this notation okay with everybody also? No? Or yes? Yeah, right? So you learn. So 0.005 is smaller than my tail, but my tail is also smaller than 0.010. Okay, so we just know my tail area is in between these two numbers. Is that okay? All right, so let's just try a few examples here. Okay, so.
Can you go back to 1 second, please?
All right, give me a second here. You're good? Okay. All right, so let's say, so tell me the tail area if, okay, so your test statistic is equal to 1.94 and your degrees of freedom is equal to 8. 8 degrees of freedom . 1.94. I get that my tail is between 0.050 and 0.025. Is that what everybody got?
Yes.
Anybody have issues with that? Okay. All right, so tell me tail area if your test statistic is equal to 2.46 and degrees of freedom is equal to 58. Mm-hmm.
Is the lower value always going to be on the left side?
It doesn't matter. Okay, so I got my tail areas between 0.005 and 0.010. Is that what we got?
Yeah.
Okay, so because we don't see 58 degrees of freedom in the table, we'll use 50 degrees of freedom. 2.46 is in between 2.403, 2.678, and so my tail area is between 0.010 and 0.005. Okay? Does the smaller value always have to be on the left? No. You could write 0.010 tail 0.005, but how are your signs pointed? They have to point this way, right? So either form is fine. These are identical. Okay? These are allowed. Either form is allowed. Not allowed would be to write 0.010 less than tail less than 0.005. Okay? This is wrong, because there's no world or no set of math where 0.005 is greater than 0.010, because that's what this is saying. This is not allowed. Okay, is that okay? All right, let's try something else out. Okay. What if, tell me the tail area if your test statistic is equal to 4.62 and you have degrees of freedom equal to 13. What is your tail area? So you have 13 degrees of freedom and your test statistic is 4.62. What is our tail area?
So it's going to be greater than 2.001.
No. Our tail area, here, let me, is less than 0.001. Okay? This is my answer here.
Can you put 0.001 is greater than tail?
Okay, if you want to write 0.001 is greater than the tail, that's fine. They're, again, identical. But do not write, not allowed, would be tail is greater than 0.001. Okay, this is wrong. Is that okay? So we look at 13 degrees of freedom, and we see that 4.62 is bigger than 3.852. It's bigger than our last number in the table. And so that means we are more on, we're going to be on this side. So 4.62 is over here. So that means our tail area is over here. Okay? And so don't get confused, but the closer your test statistic is to 0, the more you have in your tail area. The farther you get away from 0, the less you have in your tail area. So at 4.62, we're further away than 3.787. That puts our tail area smaller than 0.001. Is that okay with everyone? I hope. Okay, so just one last one. Okay, what is your tail area if your test statistic is equal to 0.61 and degrees of freedom is equal to 4? Okay, so I'm getting my tail area is greater than 0.100. Okay, or just greater than 0.1. Is that okay with everyone? Yes or no? Okay, great. Okay, so this is how we use the t-table. We're going to make use of the t-table a little bit later today when we go over confidence intervals and hypothesis tests. Okay, so I showed you 2 ways to use the t-table. One way is for confidence intervals, and the other is for hypothesis tests. Okay, so make sure you keep everything straight. Should be okay. Okay, so let's cover confidence intervals first. Okay, so for a confidence interval, what we do is, so let me just start off with confidence intervals. Okay, and I'm going to split everything up here. Okay, we have confidence intervals, and today we are all dealing with numeric variables. Numeric variables. And for our first case, we're going to have just one sample. Okay? So this is what we do when we have confidence intervals, numeric variables, one sample. Okay? Okay, we want to make a confidence interval for the population mean mu. Mean mu based on our sample. Okay? So statistics is about making conclusions from limited data. Our limited data is just our sample. We are making conclusions about the population mean mu. Okay. So this is the formula.
What does CI stands for? Confidence level?
Confidence interval. Okay. CI, confidence interval. Okay, so the formula for the confidence interval for a confidence interval. Okay, again, numeric variables, one sample, is going to be x bar plus or minus t star times s over the square root of n. Okay? That's it. Okay? Let me just give you some labels of the different things. Labels of items in the formula. Okay. X bar, this is your sample mean. It's also known as our point estimate. Point estimate of mu. It's also the center of the interval. So if I asked you, what is the center of the interval? The answer you would give me is the value for x bar. Okay, so these are all different labels of the things in this thing. Okay, t star, this is our critical value. Where do we get t star? T star comes from the t-table. Excuse me. Okay. S over the square root of n. This is known as our standard error. And the quantity, t star times s over the square root of n, this is known as our margin of error. So these are all terms or labels that you should be familiar with. Okay, so let's do an example here. You guys remember confidence intervals for proportions with p-hat? That was from 2 weeks ago. It was on your quiz from 2 weeks ago. Okay, so it's similar, right? It looks a little different. The formula looks different, but well, maybe we'll see that it's similar. Okay, so here, let's do an example here. So when you do a confidence interval, you get two numbers, right? A lower and an upper. Okay, same thing, right? We do the plus and we get the upper. We do the minus and we get the lower. Same idea here. Okay, so let's do an example. Okay. We wish to know the average age of someone who graduates high school. Okay. We survey, let's say 84 randomly selected high school graduates. Okay. And ask how old they were when they graduated high school. Okay. The average of these 84 students, or 84 people, is 17.92 years old. With a standard deviation of 0.59 years. Okay, what is, so I'll say make a 95% confidence interval for the average age of graduating high school for everyone in the population. Graduating high school for everyone in the population. Okay, so again, let me just read this out loud. It says, we wish to know the average age of someone who graduates high school. We survey 84 randomly selected high school graduates and ask how old they were when they graduated high school. The average age of these 84 people is 17.92 years old, with a standard deviation of 59 years. Or I'm sorry, 0.59 years, 59 hundredths of a year. We want to make a 95% confidence interval for the average age of graduating high school for everyone in the population. Does that make sense? Okay, so let's go ahead and do this. Let's identify numbers in our problem here. Okay, what is 84? 84 is n, okay? So I'm going to just write n is equal to 84. Okay, what is 17.92? Yes, 17.92 is our sample mean, right? So x bar is 17.92. What is 0.59? Huh? Yeah, S is 0.59. Our sample standard deviation, S. Okay? So if we're going to write our formula here, I've got 17.92 plus or minus t star times S 0.59 divided by square root of n, square root of 84. Okay, t star comes from our t table. Now we need to know the degrees of freedom. So listen up, this is how we determine degrees of freedom. Okay, so I'm going to put this up here. Degrees of freedom is equal to n minus 1. Okay, so in this for numeric variables, one sample, degrees of freedom is n minus 1. So how many degrees of freedom do we have here? 83 degrees of freedom. Okay, so go ahead and look in your table and tell me what we use for t star. Okay, we use 1.99, right? Do we see that? We go to our t table. We go to 95% confidence, 80 degrees of freedom. We always round down, 1.99. Okay, so I'm going to have 17.92 plus or minus 1.990 times 0.59 over the square root of 84.
Wait, how do you get 83 for the DF?
Degrees of freedom is n minus 1. Okay?
You did the T star.
Getting the t star, 1.99. So my degrees of freedom is 83. That's okay, right?
Yeah.
Okay. So when I go to my table, I'm looking for 83. I don't see 80. I always round down. So we're going to use this row, 80 degrees of freedom. And I'm going to the column that says 95% confidence. So that's this middle column right here, or third column. 1.990. Is that okay? Okay, and so now let's plug this all in. So leave the 17.92 and just figure out your margin of error first. So I have 17.92 plus or minus, and I'm going to type in 1.990 times 0.59 divided by, I'm going to hit the square root button of 84, close the parentheses, hit equals, and I get 0.128. Okay? Is that all right with everybody? Okay? So if I do 17.92 plus 0.128, what do I get? I get 18.05 or 048. So the upper bound, 18.048. And on the lower bound, 17.92 minus 0.128, 17.792. All right, is that okay? So I'm running out of space here, so I'm going to just flip to the next slide to say, I just want to make sure everybody's okay with how I got the upper and lower bound here.
Hold on 1 second.
Here, actually, before I move on and do the interpretation of the confidence interval, let's just do some quick drills. You don't have to don't shout out your answers, but think of the number that that you would respond with. Okay, so if I say, what is the margin of error, you would say, don't shout it out, but the margin of error is, okay, now think of the number. What is the margin of error? Okay, and what's the answer there for the margin of error? 0.128, right? It's the t star times s over the square root of n, so it's this entire thing right here, 0.128. That's your margin of error. Okay, if I asked you, what is the center of the interval? What is the center of the interval? Your answer would be 17.92 for the center of the interval. The center of the interval is x bar, so you would know that the center of the interval is 17.92. Or if I said, what's the point estimate of mu? Okay, 17.92. Critical value, what is the critical value? 1.99 t star. Okay, so you got to know all the labels of the different things in a confidence interval. Are we good? Everybody have this all written down? Okay, so let's talk about the interpretation of this interval. All right, so we just made a confidence interval, okay? So our 95% confidence interval for mu, what is mu? Okay, but the mean what? So in our problem, this is the mean age at which a person graduates high school. Okay. So our 95% confidence interval for mu, the mean age at which a person graduates high school, is from 17.792 to 18.048. Okay, so I write something like, I am 95% confident that the average age at which someone graduates high school is between 17.792 and 18.048 years old. Okay. Does that mean everybody who graduates high school is between 17.792 and 18.048 years old? No. This is a statement about what? It's a statement about the population mean mu. Okay. it is not interesting to make statements about your sample, because that's just descriptive statistics. It just comes directly from the sample. The whole point of inferential statistics is to take your limited data, which is your sample, and then make conclusions about the population that we cannot observe directly. So we didn't have to survey every single high school graduate in the world and ask, when did you graduate high school? We only had to look at a sample of 84, but based on this sample we can say the average age at which someone graduates high school is between 17.79 and 18.05. Okay? So if somebody says, do we have evidence that the average age of graduation is not 18 years old? Do we have evidence that the average age of graduation is not 18 years old? What do we say? Yes or no?
Yes.
No.
Okay, and so the answer is no. Why is it no?
Because we have evidence in the upper is 18.048.
So 18 is within my interval. The number, the value, 18.0. Here, let me. The value, 18.0, is within the interval. Meaning it's between 17.792 and 18.048. Okay? So we do not have evidence that it is not 18 years old. Okay. What if someone asks, does the confidence interval provide evidence that the average age is 18 years old? What do we say there?
Yes.
Yes? No? Okay. So over here the answer is no. Okay, and over here the answer is also no. Okay? And so even though 18 is within their interval, okay? (18.0) is within the interval. Okay, our interval is never able to. Our interval is never able to pinpoint the average to an exact value. Okay, so we're always making a confidence interval. All we can say is we're confident that the value is between here and here. Okay, we can never say it's exactly this one particular location. We can never say that. So if somebody says, well, does your interval provide evidence that it is exactly 18 years old? Your answer is always going to be no. Okay, if they said, can your interval provide that it's exactly 18.0123 years old? The answer there is also no. Even if that value is within the interval, all you can say is that the value is between here, 17.792, and 18.048. And in fact, we're only 95% confident that it is, okay? It could actually be outside of that range. It's just that based on the data we have, we're 95% confident that it's between here and here. But it may not necessarily be so. Okay? Let's say someone asks, does the confidence interval provide evidence that the average age of graduation is not 19 years old?
Yes.
Our answer there is
Yes.
yes. Okay? 19 is not within the interval. So we have evidence that it is not, that the average age of graduation is not 19 years old. Is that okay with everyone? Okay. This should seem familiar from all of the types of conclusions we made when we did confidence intervals for one sample based on the proportion p hat, right? So we took a sample proportion and we got p hat, and based on p hat we made a conclusion about what quantity or what letter? Anybody? So in chapter 6 we did confidence intervals based on p hat about the population proportion p, right? Okay, just say yes. Pretend, make me feel like you guys remember, okay? So, and we made conclusions about p based on the sample and sample proportion p hat. And they were very similar to this, right? Except it wasn't 18 years old. It was like, is the proportion 37% or not 37% or this and that, okay? It was about a percentage or proportion. But the same types of conclusions and the relationship between the interval and the conclusions there still apply here, except the only thing that has changed between what we did then and here are the formulas, okay? Over there, for proportions, it was p hat plus or minus z star times the square root of p hat times 1 minus p hat over n, okay? You had a different formula, but same idea there, okay? All right, why don't we take a short break, okay? We've got a lot to cover, so please get back here on time. We'll say I'm gonna get started at 9 o'clock whether you're here or not, okay? So come back on time. We got a lot to cover in this last hour.